go. Not sure if I see a few views on YouTube. Again, the recordings are linked in, well, the pointer to my playlist on YouTube is linked in Moodle near the top. And I don't link each individual recording, but they're in a playlist. So go there and find a lecture, and I do them in the first half and the second half, just kind of keep the sizes smaller and easier for you to navigate around and that type of thing. All right, so let's go ahead and get started again. Okay, so all right, so now we're going to compile the member function, the compile member function of the model class, builds the model given an optimizer, loss function, and metrics. Right. So an example of an optimizer is Atom. It's very commonly used one, very effective, and that optimizer determines how to actually go through that propagation method and how to step towards, how to look at the results, how to step towards updating the model parameters in order to minimize the loss. Okay? So, and then our metrics, essentially like accuracy, are used to evaluate the model performance. Okay? So, all right. So let's see. Do I not have an example of that? I guess not. So then we would fit the model, and the fit function accepts training data in the form of inputs and outputs labels, and the number of epochs used to evolve the fit. So this is where the training actually happens. So you're fitting the model to the data. And so on each data line or row of data, the system will do a forward propagation and a back propagation. And or it'll do the forward propagation on all those, calculate a cost function, and then do the back propagation, and trying to optimize that. And one whole pass around that will be an epoch, and then you're going to repeat that. And when you first start, you'll probably initialize randomly all your weights and biases throughout that whole network, right? And if you have hundreds of neurons and dozens of layers, then you're going to have lots of these weights and biases to initialize, right? But initializing randomly is normally done, and then each iteration or each epoch is going to build upon the previous one, right? So you should get better and better, and as you get closer and closer to perfection, right? The global minimum of the cost function, then your convergence will slow down, but you'll monitor that by evaluating the metrics, right? So once this thing is called, it's going to start the processing. Now we're actually calculating, right? So it's going to predict the outputs from the supplied inputs, and it's going to use the loss function each time to compare the predicted outputs with supplied outputs. That's for each row in your data set, and then it's going to average those, or calculate the mean, let's say, for your cost function. And then that's what the optimizer used to adjust the model parameters and back propagation. We'll evaluate the metrics, we'll probably print those out so you can see how you're doing. And then we're repeating that for some number of epochs, right? So this whole fit model, this is where now you're potentially, if you're renting time on a cloud, then this is where it's going to be consumed, and this is where it's going to be a time-consuming and possibly money-consuming process. So Then we like to evaluate these things, right? So a separate test data set is used to check how well the fit generalized versus simply memorizing or overfitting to the data. So the evaluate function accepts these test inputs, right? So these are separate from our training data, right? So we might have X underscore train and Y underscore train, but now we're working with this test. And we'll evaluate that, and that's going to print out how well of a job, right? So we may have specified accuracy for our metrics, and it will evaluate that, right? So low accuracy when the training fit, when training or in that fit method. So if we have a low accuracy result out of this evaluate, but we were getting high accuracy while we were training, that kind of means that the model did not generalize very well. It may have just memorized and overfit to the data, right? So if while we're training and it's outputting these metrics for the training data set, and it hopefully we're getting a high accuracy, but then when we evaluate it on this test data set, if we get a low accuracy, that's a problem. Ideally, we want both of these to output high accuracies. All right, so I mentioned hyperparameters a few times. So the backpropagation trains the parameters of the model, right? So the weights and biases might be, for any particular layer, there might be some other things that are trained, but you just think of those as aspects of the model itself, right? So backpropagation is training all those parameters. But then there's things like the learning rate or the number of neurons in a layer or something like that, right? So these are called hyperparameters, and we can use tools such as Optuna to optimize these. So let's see, did I click through on that? Let me just go here. Okay, so here Optuna is this open source type of thing. You can go right to their GitHub, but the idea is that it is going to help you optimize over, well, very generically, it allows you to optimize things, right? But what we use it for is to optimize over these hyperparameters. So it's going to explore uh, these different spaces, and it will try to figure out what's leading to encouraging, promising results, keep those, and kind of throw away those that approaches or search parameters or parameters in our hyperparameter set as it explores that range of hyperparameters and finds, that's a bad direction ahead. So then it prunes those off and no longer goes that direction, right? And it can parallelize that if you've got a big enough GPU farm. So just kind of a handy thing there. So let's get back here. And then I mentioned this a little bit, bears repeating, generalization versus memorization. The challenge in machine learning is getting the model to generalize so that it can respond reasonably accurately when provided with data that has never been trained on. Right? So this idea of overfitting can lead to memorization. So we need sufficiently diverse and plentiful data relative to the model complexity, right? So we need to kind of pair these up a little bit, right? So there's a lot of rules of thumb, but maybe some of those from the past are put into question. It's an active area of research. So just kind of be warned, right? And as you're, as a practitioner, you might run into, you might work with an organization that's got some kind of handy rules of thumb to trade off model complexity and the size and diversity of your data. And maybe those rules of thumb still work, and maybe they don't. I don't know. So, all right. So that's real quick. The basics of neural networks, Python. I know some of y'all have had some exposure to Python. Maybe you're an expert at Python, but when I did survey on the first week of class, I did see that a number of students didn't. So hopefully, if you've had Python before, you're seeing a lot of familiar stuff, and maybe you learned something new. If you haven't had Python before, my intention here is not to make you an expert Python programmer, but to get you to the point where you can try to be productive in any assignments or projects that you're building around this course, right? So now we're going to look briefly at image classification, look a little deeper at object detection, talk about metrics a little bit, segmentation. I don't think we're going to get to these in this lecture, so I've only got a couple of slides on those. I should have updated this because we're going to talk about convolutional neural networks first, right? So here, convolutional neural networks are modeled after what we know of the human visual neural system, right? Going from our rods and cones in our retina to our parts of our brain. I'm not a neurologist, neuroscientist, so I'm out of my subject area, but it's trying to do things the way we understand them, right? So and we're in this process, we're going to find that these type of networks, they're going to help us deal with translation and scale invariance. Okay, so what do I mean by that? Just real quickly, consider the idea where you've got a picture here, right? And now we're looking at all these pixels, and we've got this system trained to find these people that look like stick figures, right? And so, all right, so we can look for that little pattern in pixels, right? And so we're looking for that kind of sequence of patterns in pixels. But what if instead of being over here and that size, it's over here and much bigger, right? So if we're really too focused on matching up, this spacing and a circle this size and arms like this and that type of thing, what if we see something like that? It's we need to deal with scale variance, or we need an algorithm that handles or it is scale invariant, right? So and that it's not always going to be in this corner, it might be over here. Maybe we even want to deal with rotation and that type of thing. It's a little more complex, but you hopefully you get the point in that we can't just build a model that looks for something like this. It needs to be able to handle different sizes, and maybe this person's standing a lot closer to the camera than this person is, and or maybe they're just a bigger person, right? But we want to be able to classify both of these as people, right? And, I'll leave that for later. So probably you all have taken, your signals courses by now and have been exposed to the idea of convolution, right? So in math courses and in your signals courses and looking at signals and systems, and we do convolution a lot, right? But as electrical engineers, maybe to date, your convolutional work has been kind of in one-dimensional signals. Now we're going to talk about spatially convolving a filter over the image. So instead of over time, it's going to be in space, and we're often going to be working in 2 dimensions. So how does this work? All right, let's just look at mathematically what's going to happen. Here, I just kind of randomly pick numbers that represent pixel values from 0 to 9. So it's just single digit. Normally, these would be, of course, much larger images in real life, and these might run from 0 to 255 in terms of values, and maybe each of these has, maybe there's 3 sets of these matrices for red, green, and blue pixel values. But okay, so that's kind of how you might translate this to the real world. But in our case here, we're going to just deal with a 6x6 matrix or array of pixel values that range from 0 to 9. And I just threw these out here. This doesn't represent a real image. Now we're going to convolve that, right? So we've got this little convolution symbol here. And oops, no, I didn't need a pen. I'm going to point here. Okay, so we've got our customary convolution symbol. Here we have what can be considered a filter. Right? And we're going to convolve this filter spatially over this. These are the parameters or the values in this filter. Here, this filter is a 3x3 array. And I've got 0, 2, 1, 1, 4, 2. Okay, some values. Again, I just kind of randomly picked those. There's more to it. You wouldn't just have random numbers, but we're going to convolve this over this input data spatially. And so in your signals courses, this might have been your filter, right? So it might be like a sine x over x, or a rectangle function, or a weighted version of that, right? And it would be in 1 dimension, and typically for a normal like radio or audio signal. But here we're doing a spatial analysis. So how does this work? Well, we're going to take we're going to start with our filter here at, I'm going to say this is the origin, right? And this is going to result in each of these filter coefficients being multiplied item by item over this overlap region. And then we're going to sum up the results. So now someone can check my math. I did not double check it, but hopefully that adds up to 87, right? So how do we get that? That's 3 times 0, right? Plus 6 times 2, plus 2 times 1, plus 7 times 1, and so on, right? And multiply all those individual terms out, sum them up, and we get 87. We're going to put that right there. Okay. Now we're going to step over, right? Remember, convolution is this sliding process. We're going to slide things along. And so now we're stepped over in one direction, and we've done the same thing. Now it's 6 times 0, 2 times 2, 5 times 1, and then the next row, and then the last row, right? 7 times 1, 4 times 3, 6 times 0. And sum all those up, that's 58. We put that number there because we stepped once in the horizontal direction. We do that again, and hopefully now you figured it out. We get the answer 60, and now we do it one more time, and element by element multiplication here where they overlap, and we get 34, right? So now we would slide this filter down a row and do across again, slide it down a row, do across again, and then finally slide it down a row and go across again. And so you should get all of these different numbers. Now our operation is complete. Okay, so pretty straightforward, and you can see why it's called convolution. A couple of things of note here, and that is in signals, you might remember that we would take this filter and we would flip it. We would time reverse it first and then start our sliding and go across, right? And well, we don't do that here. Wouldn't make a whole lot of difference because you just kind of change your coefficients, right? So that's just, it's not a strictly mathematical convolution, but that's what we have here. So then note also that this output array is smaller than this input array. Okay, and again, this is our filter, but this is our input data, and this is our output data. So this has been shrunk. Why? Well, because we started with the filter in this coordinate origin right here. What we could have done, maybe what we would do, in your signals course, when you're convolving a filter over input signal, is we would start with no overlap, right? And then maybe we would have this right-hand column, this 1, 2, 0 overlapping with the 3, 7, 7. And then we would have a value out here. And then we would step, so we'd have 2 columns overlapping. So now the 1, 2, 0 would overlap with 6, 8, 7, and now 2, 4, 3 would overlap with 3, 7, 7. And but then there would be no overlap with the 0, 1, 1, so they would all be zeros. And we'd have another number that we could fill in here, and then we finally get full overlap. And then finally out here, after this step, we could continue on and overlap minimally in this direction, right? So, but also maybe as we step down, right, we might start up here. Instead of starting here or here, we might start up here, right? And then we could conceivably then get an output array size that's the same as the input array size, right? So there's options to do that. And sometimes you do it this way, sometimes you do it the other way. I'm not sure that there's a methodical way of figuring out which is the best, but it's something to try, right? And so this is kind of common just to kind of ignore that. And because one of the things we find in neural nets in general is that if we force the system into lower dimensions, then it helps it generalize better. If we keep things all at the same dimensions all the way through, maybe that doesn't even fit our purposes, right? Maybe we're trying to take an image and result that, evolve that to a decision. Is that, cat, dog, or bird, right? And well, that's just 3 values, 0, 1, or 2. Well, we might map those choices categories into, right? And so we want to shrink the dimensions of the problem. But also, even with just pure image analysis, that as we kind of shrink the dimensions, we force the system to really generalize. And that has there's a popular technique now. So convolutional neural nets have been around for a while. A little bit newer technology, at least in application, is what's called an auto encoder, and there we start with large inputs and we keep kind of reducing through various operations, different types of layers, and we reduce it down to a smaller dimension data, and then we kind of do the reverse of that. We kind of blow up the size, and sometimes if you've seen the term autoencoder in some of the literature you're looking at, then what you'll see is an input dimension that's large, and it'll get squeezed down to a smaller dimension, and then as you go to more layers, it blows back up again. And autoencoders, I've used those in anomaly detection, so you can kind of train something that looks for what might be normal, and it can kind of figure that out. And if you provide it with some abnormal data, maybe you'll get some signals or flags that, hey, this is abnormal data. So autoencoders are useful for there. They're useful for a lot of things. But so the point here is that, yeah, we're kind of reducing the size. You don't have to. You could change your parameters on this convolutional layer to keep this the same size. But sometimes it's useful for it to actually shrink. So you're forcing the system to learn more kind of higher level concepts out of all this detail. Right? So now I chose some random numbers here. Right? These numbers can be trained. So you can put this into your overall system, and you can train these values. You could think, though, now what if I wanted to figure out vertical lines, right? To find some vertical lines in this image. Well, what I might do is I might set some zeros here and some ones there, and maybe some zeros there or something. I don't know. But you might put large numbers here or even larger numbers here, right? The point is these might be all zeros, these might be all ones, and this column might be all twos, let's say, just whatever. As you're sliding this thing across, what you're going to be doing is you're going to be kind of highlighting the vertical lines, right? So if you got a line running through here, it's going to kind of get amplified, whereas things running in this other direction will not, right? So there's some examples online you can see of this. And this is actually kind of a common approach that is even outside of convolutional neural nets or neural nets in general or deep learning. You might use this filter in just a regular computer vision application, maybe built using OpenCV, Open Computer Vision. OpenCV is a library. And so you can specify, create this filter to accentuate vertical lines, or you can do another one that would accentuate horizontal lines. You might do another one that accentuates diagonal lines, right? And you might run one of these into this, and then you might also have another filter here that you can evolve that, and you output another matrix out here, right? And then another one that's diagonal lines for a filter, and that might produce another matrix that is highlighting diagonal lines. So then we can kind of concatenate all these together, and that might be kind of a super layer that then is provided to the next step in this neural network, right? And so then you might end up with this region of data that is highlighting features that have edges, and in particular edges that are running vertically, and then another one that's looking for edges that tend to be horizontal. I'm sorry, and then another one that tends to be diagonal. Right. So now we've kind of taken this just range of a whole bunch of pixels, and right now, our eyes see things, right? But we're doing all this processing all in our brain, and but we have to teach that computer how do we take all these individual pixels and try to make sense of them, try to look for features, right? So features might be these lines, they might be corners. Lines tend to show up where there's a steep derivative in the pixel values that have some consistency in a particular direction, forming a line. It could be an arc also, but a simpler idea is looking for these lines or even a corner, right? So this is kind of, hopefully giving you this idea of how does this convolutional neural network do anything? What is it doing, right? So it's mathematically, it's doing this convolution of a filter, spatial convolution, right? And but at kind of a higher level, we're extracting features from these kind of whole mess of pixels, right? And we're trying to find some structure or features in those and kind of providing those to the next set of layers. Right? So that's this convolutional neural network in big terms, right? So as I said, the filter coefficients are trained in the backpropagation process, and CNNs can learn image features such as edges and corners, and then these features are then used to recognize types of images or objects within an image. Right. So as you start to add these layers, you're taking all those pixels and trying to reduce those into features. And then maybe your next set of features, look at how certain features work with other features, right? And if we go back to my horrible drawing of people, was that in this lecture? Yeah. So somehow this convolutional neural network is looking for this kind of circle with a vertical line and a straight line and some diagonal lines, right? So that first stage might find these edges as lines that have a certain orientation to them. And then you might have a filter that looks for some circles or arcs or that type of thing, right? And then now we need to relate those together, right? So that's going to be some subsequent layers that now take these features and try to see, oh, yeah, those diagonal lines, this one sloped this way, this one sloped that way, they kind of come together near where a vertical line does, right? And then we've got a horizontal line that crosses that and a circle on top, right? So you see that we've gone from just pixel values to these edge, line, circle type features, maybe some corners. We've identified some corners. Now we take those individual features and see how they are relating to each other, right? So that's super hand wavy and high level, but I think it's helpful to understand that, yeah, how does all this process, all these equations and or function calls and programs actually implement all this stuff, right? So, all right, let me step out of this briefly, and now, all right, so let's now step back and look at Keras. Again, Keras is this thing that, for the most part, is helping you with TensorFlow. Now, it can also do PyTorch and that type of thing, right? So, so it's not restricted to TensorFlow. These are backends, different backends that it's using, but it's this API that's helping you develop things, right? So here you can go in and look at all the details of layers, models, losses, metrics, optimizers, and whatnot, right? So here's a few of them. Here's the layers, and we've got this base layer class, and then so you can use that to create your own specific layer, right? But we don't do that a ton, right? But just note that, yeah, you can use this generic base layer class and do some very, customized specific stuff. Then you've got all these different activations that you can use in these, right? So we saw the ReLU function earlier here. So, and you can even fine tune it as some different options. We looked at sigmoid more last class, and we haven't talked about softmax yet, but we will. And then I've talked about how when you start the process, you start right at the very beginning, you might just normalize everything or randomize all your weights and biases, your filter coefficients now in convolutional neural networks, any other model parameters. At the very beginning, you might just randomly initialize it. Where your random numbers might be picked from the normal or Gaussian distribution or the uniform distribution, or you might try to do some more fancy stuff, right? So, so then we have, I'm going to skip over some of these because we're not ready to talk about those. We have core layers. So we've talked about the input layer. We've done the dense layer. And you've got a few other kind of core, very basic, simple neural network type layers, right? So here's the dense, and okay, so I hesitated to call it simple, but I couldn't find a better word for it, right? That's why I was stumbling a little bit, because it's not, right? There's lots of things you can do to be a little bit more sophisticated with it, right? But generally, it's fully connected layer, right? Neural network layer. And but then here we have our convolutional layer. So you can do a 1D, a 2D, or a 3D, right? So here we've got the various different things that you would specify with a 2D layer. So the kernel is the sometimes used as that filter, right? So we see here, this is the int filters is the dimension of the output space, or basically the number of different filters in the convolution. That in the case I was briefly describing earlier, where we're looking for vertical lines, horizontal lines, and then positive diagonal lines with that basically 45 degrees of positive slope. That would be three. That would be three different filters, right? And then kernel size would be the size of those filters, right? So in the example, those are 3 by 3, right? So you put in 3 there. Strides is the idea that, well, we when I showed you this, I stepped this over 1 pixel at a time. Well, there's options to skip a pixel every other time or more. And so you might find that you want to reduce the dimensionality really fast. And so you'll stride, and you'll basically stride over some of these columns and rows as you slide this filter across, right, and up and down. So that's at strides there. And padding here describes it can be valid or same, and valid means no padding. So what I describe in my slide, PowerPoint slide, is valid. Same is what I was kind of describing, that if we offset the thing so that we're starting up here instead of starting right at the origin, we start with maybe zero overlap, and we do that in the way that the output is the same dimensions as the input, so it's the same, right? And so that's an example. You can use either one. Valid means no padding. Same, we're going to result in padding evenly to the left and right or up and down of the input, such that the output has the same height and width dimension as the input. Remember, this is a 2D layer, so we're going to have the concept of a height and width in these things, right? So lots of other things here that we can tweak with. Again, not so simple. Lots of different things to look at, right? But those are kind of the biggies. And then when we talk about deep neural networks, we'll talk a little bit more about pooling and regularization. I thought I saw that somewhere. Regularizers and these are the more common regularization layers and normalization layers. So there's so you can see that convolutional layers are pretty important, and so you've got a few different ones of these. Then we saw in the little example I gave you earlier on using Keras, is that I think we had some different type of pooling layers, maybe a max pooling or global max 2D pooling or global average or something like that, right? So so here, this max pooling 2D layer is a max pooling operation for 2D spatial data, downsamples the inputs along its spatial dimensions, right? Height and width in this 2D case, by taking the maximum value over an input window of size defined by pool size for each channel of the input. The window is shifted by strides along each dimension. All right, so I don't really have a description of this, but you can think of this as, instead of being individual pixel values or filter or kernel values, now we're going to have a function in here, right? So if we're going to, so if we're going to overlap at this point, now we're and ignore these numbers here, because this is going to be a function that is going to find the maximum value in all of these values here, right? So that'd be that 8, and we would put an 8 right there, and then we might shift it over once, or we might shift it over a stride of 2 and go over here, and now we would look at the max and we'd see that's 6. So that would be a 6 right there, right? If we didn't stride, the max here would be 8. So I think we'd have 8, and then 8, and then 6, and then another 6, right? So 8, 8, 6, 6. If this was a max pooling, right? So we're going to have a certain size to this, which should determine how many pixels we're going to look at to calculate our max. And then we can have a stride also that determines how we step across. Okay, got a little bit of time left. So, all right. So, what else do I want to show you? So, Recurrent layers are often used for signals, audio, or speech, or that type of thing by this long, short time memory type things. We probably won't have time to look at those, but these feed back some stuff to earlier parts in your layers, and so it kind of has some recurrent behavior to it. Normalization and regularization are also important, and this becomes a bigger deal when we go to many layers, right? And what can happen is that our derivatives and our values, as we march through a either in a forward or the backward propagation direction, can get smaller and smaller or bigger and bigger. And so we might want to normalize those. And we use regularization to try to help prevent too much overfitting and memorization, right? So the dropout layer randomly sets input units to 0 with the frequency of rate, right? So I think in our example that was 0.2, right? So at each step during training time, right? So as you're training, as you're going through this process, you're going to randomly set some of the input units to 0, and it's going to change each time. And so we're basically going to ignore those parts of things, right? Well, that makes sense in kind of a practical level, because yeah, think of this idea of trying to find a pedestrian, but he's or she's partially occluded by a bush or a sign or a bicyclist or another car or something like that. So you're only seeing part of them, right? So they don't look like a full pedestrian or human, right? So again, that's a little hand wavy, high level, but trying to give you a little bit of a way of relating some of these things to the real world, right? So we typically do dropout only in training. And then, so each of these training iterations, it's going to randomly pick some inputs to 0 out. But then as we, when we switch over and actually use that model in inference in production, let's say, and let's say we've installed it on a car now and we just expect it to work, right? We're not training it anymore, we're using it. And we're trying to get inferences out of it. Well, we don't want to ignore anything then, right? So we're going to use all our inputs, and we're not going to do dropout. It would be rare to use that in inference also, right? So, all right. So I mentioned the losses, right? So here's a whole section on probabilistic losses, and it's just got a bunch of them, right? So these categorical cross entropy class is a common one, and so we'll see if we have time to go a little bit deeper into that, but you see most of these are built for you already. We talked about max pooling, 2D, and again, you have this pool size, strides, and here we're saying it's 2 by 2, right? So we're going to look at 4 pixels each set. That's the default. It's expressing the defaults, but we could pass in different values there. We could set a stride of 2 or something like that, right? And again, we can do this padding, valid or same, and so on. We looked at this, I think, already. So we've got this convolutional 2-dimension, and then we already looked at that. All right, so that was a bunch of that. All right, so we've got 15 minutes to go. I keep So I'm going to here. I'm going to put this in the chat, and whether this is useful to you or not, but it's just something to look at again. Hope I'm still closed out too many things here. All right, so this is someone's example of object detection with RetinaNet, right? So here it's been authored, created back in 2020. It's been a fun COVID project, I guess. So, but he's implementing some particular type of detection, object detection, right? So Google Colab is similar to this Jupyter notebook, but you're running on their server stuff. So we can import these. OS helps you look for files. It's basically operating system type utilities. We've got NumPy, TensorFlow, and Keras, and Matplotlib, and so you're seeing a lot of common themes here, right? So unfortunately, I think this thing takes too long to train, but it's again giving you some examples to look at. So here they're talking about this COCO 2017. So there's these COCO data sets, and they have all sorts of different objects in them, images, and so there's a few different ones of these, but they're very classic training data sets to use. 118,000 images, so we're just going to download 500. And so hopefully it didn't disrupt my my streaming to you too much, but so it took 35 seconds to download that. And then here we've got some functions that he's declaring and that type of thing. Then he's going to compute this pairwise intersection over union. And so I think I just wanted to kind of show this to you before we ran out of time. You can kind of go through all this. I think this should just run through. And here, building up what he calls a feature pyramid, right? So here's the ResNet 50. So we looked at a very simple ResNet earlier, and but here's this ResNet 50, and it's so famous you can just load it, right? And it's already got pre-trained weights and that type of thing. So all right, let's get back to this. So I just wanted to introduce that because we're going to have time this evening to go into it deeply. So we talked about this convolutional neural network and how we can train those filter coefficients. We could maybe think of good ones to use, but we can just let the back propagation of the optimizer handle it, right? And figure out what are the best filter coefficients for our particular application, right? And all. So, all right. So now, what do we do with all this stuff? So, in computer vision, there's a few different classes of problems that we tend to tackle, right? An image classification is what we would call that example we briefly talked about earlier. We didn't actually run through an example, but the MNIST data set, which you can download, has all these different handwritten images of handwritten digits, 0 through 9. And they're all labeled. They had, I think it was done at NYU or Columbia or something, where Dr. McCune was from back in those days. And they had a bunch of volunteers and students just write down all sorts of numbers, and then they labeled them. And organize those into a data set. Now, each of those images only has one digit in it. And the job of image classification would be to look at that image and say what that image is, what that image represents, right? So if we build a model that assumes that we have output categories of 0 to 9, then that's our task. We're trying to figure out which class an image belongs to, either the digit 0, 1, 2, up to 9. So what we're doing here is we're assigning the most likely class ID to an image that describes the central feature in this image. So we're looking at image as a whole, saying, what is that image, right? Might be a bicycle, and we encode that to 47, something like that, right? So if you look at some of the COCO data sets, they will have all sorts of different objects, and that image is dominated by a particular thing that would have an association to a class ID. And again, it might be a bicycle that encodes to a particular number, and it's labeled with all those. So now really, how often do we use image classification in like production autonomous vehicles? I don't think that much, right? So there might be some specific applications of it, but generally we're looking at much more complex images, right? So we're looking at the road ahead of us, to the side of us, behind us, something like that, right? Let's say the road ahead of us. And we might at any given time see a whole bunch of different things, right? And we might be interested not in what the image as a whole is, but different things in that image, what they are and where they are, right? So this image classification is kind of a stepping stone to object detection, right? So if we were doing a whole course just on machine learning and computer vision, we would dive into image classification first. And then we would do like object localization, which might look at a single object and figure out where it is in an image. So now we've identified the type of object and where it is in that image, maybe by pixel location where the centroid or center of that object is. But ultimately, we want to find multiple objects in an image and their locations, right? So these are all stepping stones to object detection. So image classification by itself is limited use. I'm not going to say zero use, but limited, since really most of the images we're looking at are likely to contain several objects, and we're typically interested in knowing their location, right? So that brings us to object detection, right? So actually, I need to keep an eye on the time. We've got a few more minutes left. I want to get through a couple of 3 more slides. So now with object detection, we want to determine a bounding box that best encloses objects in the image and their class IDs. So we're going to detect the individual instances of the same class, right? And so we might have objects of different classes, and we might have multiple objects of the same class. So we don't want to, we may not be as interested in identifying, oh, that's a group of 5 people. We might want to actually localize each person in that group, right? Is there maybe people are crossing on a crosswalk, and we want to track each individual in that, right? So there's some subtleties here. We're not just looking at the centroid, let's say, or location of all the people. We're trying to detect individual instances of those of pedestrians, bicyclists, cars, trucks, right? So our input is an image. our output is 0 to n instances of 0 to m classes with location. Right now, that location is just an example. We call it a bounding box typically, but it might be encoded as an x and y pixel location of the center with the width and the height of the rectangle that best bounds or encloses these objects that we're detecting. Okay. Now you could include some rotation. You could use other parameterization. Maybe the x and y might be the center, or it might be the top left, or lower right, or whatever. Right. So here's an example. So just grab this image, and now we're have a bounding box on this car here, right? So here I tried to draw them pretty accurately, right? And don't assume that your algorithm is going to be as good as a human might label it, right? So we've got to estimate what is the best bounding box that surrounds this car. Oh, but there's a car there. There's a car there. There's a car there. I think I missed one back there. There's a car there. So we're trying to draw bounding boxes around each one of these. Now, I've also kind of drawn in probabilities, right? So I just made these up, but the algorithm in this case is identifying this car with 90% confidence, or probability, 90% probability that this is actually a car, and that this one's 87% probability. Maybe, this dumpster over here is kind of almost the same color, so it might be confused. And these are a little harder to see. This one's partially occluded on the back of it, so it makes trying to figure out this bounding box hard, and we're still kind of hopeful that that's a car, right? So, but we also have some stoplights in here also, right? So we're trying to classify these, right? So we have these different instances of the same type of object, and these different instances of the same but different object from that first grouping, right? So, and you might have a bunch of other things. Well, I don't think we have any pedestrians or bicyclists in this image, but so that's the example of this object detection, right? So we'll go into a little bit more detail on how that is done and in our next class. And again, I'm adapting on the fly, so I spent a little bit more time introducing Python and a little bit more time introducing the basics of neural nets and doing some very initial examples. We'll do some more examples in the subsequent lectures. So next week, we'll look at how object detection is done. How do we come up with these bounding boxes, and how is that done in a modern way? We've kind of evolved in our practice of how that's done, and then we'll look at metrics. I've already mentioned metrics, right? So we saw in that code example that the metric was chosen as accuracy, right? Well, at a kind of a high level thing, we might be looking at number of false positives, number of false negatives relative to true positives and true negatives. We might combine those into what's called an F1 score for object detection and segmentation. Segmentation, you can look ahead in a lecture. I've just got a very basic slide on that so far, but there's some intersection over union is a classic metric there. So, all right, out of time. Thank you. I'll hopefully see some of you all tomorrow, somewhere between 1:30 and 3 o'clock on campus. And otherwise, I'll see you next week.
Thank you, Professor. I'll see you tomorrow.
Great.
Professor?
Yeah.
I just had a question about the the radar assignment that you gave us.
Okay, let me turn the recording off.
Yeah, that's fine.